students, and today's class we are going to talk about the Henderson Hasselbalch equation. What is the significance of this equation? Actually, by using this equation, we can calculate pH of a buffer solution can be calculated. For an acidic buffer, we can calculate the pH. And likewise, for a basic buffer, we can calculate pOH. And even pKa can be calculated. And in addition to that, pKb can be calculated by using this Henderson Hasselbalch equation. So these are all the objectives of deriving this particular equation: to calculate the pH of a buffer solution, to calculate the pH of a basic buffer solution, and to calculate the pKa value and to calculate the pKb value. When we know what is called acidic buffer, consider this acidic buffer solution HA, a weaker acid. When it is dissolved in water, that would be dissociated to form hydronium ion and A minus ion, H plus A minus. The water which gives electron pair to this hydrogen, so we are obtaining the hydronium. So it's a weaker acid, gets partially dissociated. To that, when you add a stronger electrolyte like this, Na, that is completely dissociated to form Na plus and A minus. So this is the composition of acidic buffer solution. Our aim is to calculate the pH. We know what is called pH. pH is nothing but the negative logarithm of hydronium ion concentration to the base 10. So how to calculate the hydronium for a given acidic buffer solution? Consider the first equilibrium. From that equilibrium, we can determine the Ka for this, the dissociation constant for weaker acid, Ka, that is equal to, we can say, the hydronium ion concentration into the concentration of A minus divided by the concentration of HA. Isn't it, the HA? And the concentration of water is in excess, so you need not put the concentration of water there, it is understood. So H2O you need not write here as it is in excess. Now we have got the hydronium ion concentration here, and we can rewrite this as follows: H3O plus, that is equal to Ka into HA divided by A minus. So this is the expression of time now. And in this particular case, what is this HA? This can be taken as the original concentration of acid. I will explain how to take this as the original concentration of acid. Suppose if you take 1 mole of HA initially, only a fraction is getting dissociated. So the amount of HA or the fraction of HA which is dissociated is very much lesser. And moreover, here there is a common ion. You see, the A minus is common. When there is a common ion, the equilibrium is shifted to the backward direction. Again, the dissociation of HA is lower. Already HA is poorly dissociated. Due to the presence of A minus common ion, its dissociation is further suppressed. So a least quantity, negligible quantity of HA is getting dissociated. And hence, the HA can be taken as the original concentration of acid. The reasons can be given as follows. Though HA is dissociated, the fraction of dissociation is too small. Apart from this, the HA dissociation is further suppressed by the addition of NAA, which means the stronger electrolyte, the common ion. So due to these two reasons, the HA dissociation is ignored and HA can be treated as the original concentration of weaker acid in this particular expression. Likewise, the A minus, what is given here in the denominator A minus, can be taken as the original concentration of salt. You see, certain amount of A minus is obtained from the weaker acid, but the quantity of A minus obtained from the weaker acid is negligible. Most of the A minus comes from the stronger electrolyte, namely from the salt. So the quantity of A minus obtained is maximum from the NaA, not from the weaker acid. So the concentration of A minus is treated as the original concentration of salt. And this is the explanation for that. Majority of A minus comes from the salt, not from the weaker acid HA. So NaA is giving you the majority of A minus, and hence this A minus is treated as the original concentration of salt. With the help of these two, we can rewrite this equation as follows. Okay. Yes, we have got an expression like this. The hydronium ion concentration, that is equal to Ka into HA by A minus. So in this particular equation, I can write the HA as the original concentration of a given acid, and A minus is taken as the original concentration of salt. And if you do so, we can have hydronium ion concentration that is equal to Ka into the concentration of acid divided by the concentration of salt. After that, we are going to take the log on both sides. On taking log on both sides of the expression, we can have the log of hydronium ion concentration that is equal to log of Ka plus log of acid concentration by the concentration of salt. After writing this expression, now we are going to change the sign on both sides. On changing sign, in the above given expression, and you can have a new equation as follows: minus logarithm of hydronium ion concentration that is equal to minus log of Ka, and for our convenience I can write like this, plus into, I can open a bracket, minus log of acid concentration by the concentration of salt. And we know that the minus logarithm of hydronium concentration is nothing but pH. We know the definition for that. pH is nothing but minus logarithm of hydronium ion concentration. And minus log of Ka is nothing but pKa plus. Now, the salt is taken to the numerator and acid is taken to the denominator. If you invert that, the sign can be changed so that we can say log of salt by acid. We were inverted. Okay. Actually, the plus into minus is minus. And that minus is written in this form for our convenience. Plus into minus. We are keeping the plus as such. And to change this minus sign, I have inverted the salt by the acid. Salt is taken to the numerator, acid is taken to the denominator. So this is the final expression. By using this, we can get the pH value of respective acidic buffer solution. Suppose your buffer solution is basic buffer solution. And we know what is called basic buffer. It has got a weaker base like this. That would be dissociated to form B plus and OH minus. And its salt might be given as follows, Ba. That forms B plus and then A minus. And if you want to calculate the hydroxide ion concentration for this particular base, Kb into what will you do? BOH divided by B plus. Because for this Kb, that is equal to the B plus into OH minus divided by BOH. And to know the OH, we can take the expression as follows. And as usually, by taking the log and by changing the sign, the final format of the expression is given here as follows. We can have POH that is equal to PKB plus the log of salt concentration to the concentration of base in the denominator. So this is applicable for a basic buffer solution. It is for acidic buffer and this is for basic buffer. Similar procedure. By the same way, we can derive this expression. This equation is called as Henderson Hasselbalch equation. By using this, we can calculate the pH as well as pKa. By using this, we can calculate POH as well as pKb, provided if you are given the concentration of a salt and acid, otherwise the concentration of salt and base. Okay.